To observe a stable interference pattern, the wave sources need to be coherent, which means they must maintain a constant phase difference and have the same frequency or wavelength. On the left, the diagrams show pairs of waves. The top pair demonstrates coherence with waves that keep a steady phase difference and identical frequency, while the bottom pair on the right illustrates waves that are not coherent because their phase changes over time despite having the same frequency. This change in phase prevents a stable interference pattern from forming. So, coherence is essential to ensure the waves combine consistently to create clear and predictable interference effects.
The path difference is the key factor that determines the type of interference we observe when two waves meet. It's simply the difference in distance traveled by the waves from their sources to a specific point. When this path difference is a whole number multiple of the wavelength, the waves arrive in phase, resulting in constructive interference, where their amplitudes add up and create a maximum effect. On the other hand, when the path difference is an odd multiple of half the wavelength, the waves arrive completely out of phase, meaning one wave's peak aligns with the other's trough. This causes destructive interference, where the waves cancel each other out, leading to a minimum or no signal at that point. The diagram shows these two scenarios clearly. At one point, the path difference equals the wavelength, producing constructive interference, while at another point, it's half a wavelength, causing destructive interference. Understanding how these differences in path length affect wave interaction is fundamental to explaining various wave phenomena.
When two coherent sources, like these speakers, emit waves, they create a stationary interference pattern in the surrounding space. The curved lines you see are wavefronts, showing how the waves spread out from each source. The black dots mark where the waves meet in phase. This is called constructive interference, or maxima, meaning the crests of the waves align and reinforce each other. In contrast, the areas between these dots represent destructive interference, or minima, where the crest of one wave meets the trough of another, causing them to cancel out. This pattern of alternating high and low intensity regions is fundamental to understanding how waves interact in space. We begin with a monochromatic light source, which produces light of a single wavelength to ensure consistency in our experiment. This light first passes through a single slit, which diffracts the light and causes it to spread out evenly. The diffracted light then illuminates the double slits, labeled A and B, which act as coherent point sources. As the light waves pass through these slits, they overlap and combine, creating a pattern of alternating bright and dark fringes known as an interference pattern. This pattern is essential because it demonstrates the wave-like properties of light through the phenomena of diffraction and interference. When the light passes through the two slits, it creates an interference pattern on the screen, showing a series of alternating bright and dark bands called fringes. The bright fringes happen where the light waves meet in phase, meaning their peaks line up, resulting in constructive interference and increased brightness. On the other hand, the dark fringes appear where the waves meet out of phase, meaning the peak of one wave aligns with the trough of another, causing destructive interference and reducing the light intensity, creating dark bands. This pattern of alternating fringes clearly demonstrates the wave nature of light. Here we have a simple formula that helps us calculate the distance between the bright or dark fringes in an interference pattern. The key idea is that the fringe separation, labeled as S, depends on the wavelength of the light, the distance from the slits to the screen, and the distance between the slits themselves. Specifically, S is equal to the wavelength times the distance to the screen divided by the slit separation. This means that if the wavelength or the screen distance increases, the fringes spread further apart. But if the slits are closer together, the fringes get wider too. The diagram shows the two slits separated by a distance d, the distance to the screen as d, and the fringe separation as S. This formula is essential for predicting and measuring the interference patterns we observe.